Our speaker tonight, again, is Dr. Paul Debevec. He is the Emeritus Professor of Physics at the University of Illinois, where he has been on staff since 1977. His research is in nuclear and particle physics, has also included experiments at CERN and SCI in Switzerland, at Brookhaven, and also Fermilab just north of here. Very, very happy to have him with us tonight. So please welcome Dr. Paul Debevec.
Thanks so much. It's a delight to have so many people here. This energy challenge, understanding energy challenge, it takes more than science. I have a lot that I want to tell you. I've had to leave things out, major topics in putting together this talk. Even in the course of the talk, I might have to fly through some things. There's this clip about a speaker who comes to a presentation without his watch. And after a while, he asks the audience, how long have I been speaking? And from the audience, there's the reply, there's a calendar behind you. So we'll see how this goes. My introduction to the energy challenge began just about 5 years ago. I cashed in some frequent flyer miles. I went to a conference at Berkeley. It was organized by David Haffelmeister, who's actually a PhD graduate of our physics department. And energy has been my professional hobby since that time. So the energy challenge. I'm going to start with what is the energy challenge. I'll talk about supply and demand of energy in the United States and in the world. I'll give you some points of reference that everybody knows when they talk about energy. I'll give you a few examples, and then there'll be some concluding remarks and summary. So let's start. What's the energy challenge? So here are the half a dozen points about the energy challenge. First of all, energy is crucial to modern society. Secondly, fossil fuels from which we derive so much of our energy are linked to climate change. Third, our current oil supply is insecure. Fourth, the energy demand for developing economies is growing, and in fact is growing dramatically. So there'll be a competition for energy in the next few decades. Fifth, the underdeveloped world needs energy. I'll have very little to say about that. I have to get that out. There's roughly 1 billion people that have no electricity at all in the world. And finally, the world population is increasing, another topic that I'm going to have to completely leave out. So energy is crucial to modern society. So here's a complicated graph. It's worth spending a moment looking at it. So down here is GDP per capita, and up here is power consumption in kilowatt hours per day per person. And way up here, with a high GDP, roughly $40,000 per year, and with a high power consumption, roughly 250 kilowatt hours per day per person, sits the United States. And on this picture, you can see that there are other countries that are also quite nice to live in, like France and Germany and the United Kingdom. And most of the developed European nations are considerably use less energy. In fact, it's almost a factor of 2. Way down here, at roughly 150, is France and Germany. Way up here is the United States. Let's see, 250 kilowatt hours per day per person. A day has 24 hours, so that means 10 kilowatts per person. 10 kilowatts, that's like you have 6 hair dryers going on all the time for everyone in the United States. That's a lot of energy. Now, that graph came from an absolutely delightful book, Sustainable Energy Without the Hot Air, by David Mackay. You can get it for free. I'm jealous of that book. I wish I wrote it myself. And as he says, the aim of the book is to help you figure out the numbers and do the arithmetic so you evaluate policies. It's somewhat directed to the United Kingdom, but a lot of it applies to our country also. Okay, fossil fuels are linked to climate change. Let's spend a few minutes with that. So here's 2 graphs. The upper graph is the temperature anomaly from 1850 to 2000. So the Industrial Revolution started a few decades before 1850. all the temperature anomaly means, so this is the land surface temperature. This is averaged over the entire Earth, year by year by year. There's actually 4 plots here done by 4 independent groups. They agree upon the result. They set 0 between 1950 and 1980, that flat region there. And then you notice from about 1970 or 80 on, the temperature is rising. There is no debate, there should be no debate that the Earth is warming. And down here, this is the concentration of carbon dioxide in the atmosphere, same time frame, 1850 to 2005. And as you see, the amount of carbon dioxide in the atmosphere grows and grows and grows. And this is due to the fact that since the Industrial Revolution, we've used fossil fuels, coal, natural gas, and petroleum to fuel our societies. Now, how do we attribute the global warming to carbon dioxide and, more importantly, the human anthropogenic carbon dioxide? Well, that comes from a calculation, or if you want a model or simulation. So this graph here is from the International Climate Change Committee, and it's a comparison of many, many different models, about 20 of them. So the models are in the yellow. The average of the models is in the red. Black, in fact, is the temperature, and you see with man-made and natural forcing, the models, in fact, fit the history of the temperature. Now, let's take out anthropogenic. Again, there's the data. The Earth is getting warmer. There's the models. And now, in this region here, with natural forcings only. Basically, that means the sun, the orbit, water vapor, anything but putting CO2 in the atmosphere from man-made sources, it no longer agrees. So this comparison of model calculations to the temperature data leads essentially all climate scientists to say that the cause of the warming is anthropogenic, it's us. Now, have we seen climate change already in any dramatic fashions? Well, it's somewhat controversial, but you remember we've had tornadoes, we've had wildfires, we had drought. All these things happened just last year. So extreme weather is becoming, in fact, more and more likely, and the predictions of these climate models is that there'll be more and more extreme weather as the Earth warms. Now, even in our own state, just a few months ago, USDA issued the new plant boundaries, hardiness zones, and in 1990, this was the boundary between zone 6 and 5, and now in 2011, this is the boundary between zone 6 and 5. So in only 20 years, the plant boundary, the plant hardiness zone, has moved a few hundred miles. Again, evidence of global warming. Now, there's a lot on this graph. It's the greenhouse gas emissions in tons of carbon dioxide per person, and the energy use, kilowatt hours per day per person. So again, this is the energy use, and sure enough, there we are, the United States, at about 250 kilowatt hours per day per person. Remember, that's your 6 hair dryers going on constantly, day in and day out. And way up here, at about 25 tons of carbon dioxide per year per person is the United States. And you notice the United States, here again is the United Kingdom, Russia, France, and one for Germany. The United States distinguishes itself also by being a major emitter of greenhouse gases. Interestingly, there are 2 lines here. This line called natural gas, this line called coal. There is a fixed relation between greenhouse gas emissions and energy that can come from either coal or natural gas. And coal, in fact, produces much more greenhouse gas for a given amount of energy than natural gas. So if you could change completely from coal to natural gas, you would in fact reduce your greenhouse gas emissions. You'll also notice that just about every country is bounded between coal and natural gas, because throughout the entire world, energy is produced mostly by fossil fuels. There are some exceptions. Here's Iceland. Iceland has an enormous amount of geothermal energy. Oh, the oil supply. I have in my wallet the formula for what gasoline prices will be next month, but I'm not going to tell you. So where is the oil in the world? Well, the United States actually does have some oil supplies in the Gulf of Mexico. Canada has considerable oil supplies. There's Venezuela. The North Sea, shared by the UK and Norway, has quite a bit of oil. But we all know there is where most of the oil of the entire world sits, in the Persian Gulf. And in fact, here's a plot of the percent of total world oil reserves of the 15 countries on the top of the list. Number 1, Saudi Arabia. Number 2, Venezuela. Then comes Canada. And if you look at this list of countries, there comes the United States, way down there. And as President Obama noted in the State of the Union address, we only have 2% of the world's oil reserve. And this country needs an all-out, all-of-the-above strategy that develops every available source of American energy. The United States, in fact, is a big consumer of oil, a big importer of oil, and we, in fact, have control over very little of the oil. Now, I don't want to get too political here, but if you look at a number of these countries here, they have political debates about with the United States. A number of them are OPEC countries, for example. Now, in fact, there are been disruptions to oil supply. This is from BP. BP puts out every year an analysis of the energy industry. And this is from just last June 2012. The light green line is in 2011 dollars. The darker line is in current dollars, or if you want money of the day. And this is after the post-war years. The world enjoyed, in fact, rather stable crude oil prices. Then in 1973, there was the Yom Kippur War, followed by the Iranian Revolution. This big peak in oil prices is invasion of Iraq and Arab Spring. And the entire world has had to grapple with increasing crude oil prices, not only from the disruptions, political disruptions, but from the increasing demand from other countries. So here we go. Energy demand from developing countries is increasing. Now, in the dark blue here, these are the Organization of Economic Cooperation and Development countries. That's basically Europe, Canada, the United States. And the prediction is that, from the International Energy Agency, that the growth in demand from basically Europe, Japan, Canada, and the United States, that's not going to grow much over the next several decades. It increases from 200 quads to about 300 quads. But this region here, these are countries like China, India, much of the rest of the world. And as you see there, the demand increases considerably. So from 1990, in 4 decades, the demand for energy will double. And we've seen that already. So here's the United States, its energy consumption. This was put out in 2011, so anything after, I think, 2008 is a projection, or maybe it's 2010. And as you see, somewhere around that, China, in fact, has surpassed the United States in energy consumption. But we should remember, China has 4 times the population of the United States. And still, it is a growing economy. So this is an enormous increase in demand. India also has a large population. Its demand is projected to increase somewhat slower. So this, in fact, is the story that there's going to be a greater and greater competition for energy. The world population. Right now, the world population is around 6 billion people, and in roughly 4 decades, the range will be somewhere between 7 and 10 billion people. All of these people want better lives. They'll need energy for those better lives. Energy supply and demand. So let's focus on where we get the energy and what we do with it. It's quite a complicated story, but actually you could break it down into different parts, 4 parts. But one reason energy is hard, they make it difficult for us because of the different units of energy that are used. First of all, there can be very large numbers. Many people in talking about energy use a unit called the quad, which is a quadrillion British thermal units. Physicists hate this unit. The only thing good I can say about this unit is that the United States uses about 100 of them, and 100 is an easy number to remember. When you talk about oil, everybody talks about barrels, which is 42 gallons. For example, the United States consumes about 19 million barrels of oil a day. When you talk about coal, it's always in pounds or tons. When you talk about natural gas, it's in cubic feet or in therms. The power company makes it hard for you to compare your gas units to your electrical units usage, because when they talk about electricity, it's always in kilowatt hours, and when we talk about natural gas, it's always in therms. But these should be convertible, and they are. So let's take a look where the energy comes from and where it goes. So this is a simplification. A lot is put in different baskets here, but it's useful because it gives you an idea of how big our problem is, how big our challenge is. So let's look over here. What are the energy sources? First of all, petroleum. Secondly, coal. Thirdly, natural gas. Then there's nuclear. And then there's renewables. And how big one of these bars is, how tall one of these bars is, that represents proportional to how much energy we use from that source. So if you look at petroleum plus coal plus natural gas, you get the impression that something like 85% of our energy comes from fossil fuels, and that's correct. And then the question is, where does the energy go? And this particular analysis breaks it up into 4 places. Transportation, so that's cars, buses, trains, airplanes, barges, ships. Electricity, and electricity we use for many, many things. And here it comes that electricity is used for heating, ventilation, air conditioning, appliances. And finally, the third category is industrial processes. And industry, of course, needs, for manufacturing, running data centers, energy also. Now, these lines here, they go from the source to the consumption, show you where a particular source of energy is used. And you can make a simplification here. What do you use petroleum for? Transportation. And some of it goes into industrial processes, but most of it goes into transportation. Coal. What do we use coal for? Electricity. Tiny amount goes into industrial processes, but coal goes into electricity. Natural gas is, in fact, the most flexible. Some of it goes into electricity, some of it goes directly into heating, and some of it goes into industrial processes. Nuclear completely goes into electricity, and renewables go into electricity, and they go into industrial processes also. So let's review that. Where does the oil go? Transportation. Where does the coal go? Electricity. Where does the gas go? 3 places. Nuclear, electricity, renewables, electricity in industry. It's interesting to look at this electricity a little bit more carefully. Notice in this line here, you've got a big tall 40, and here a tiny little 21. What does that mean? Well, most of the generators of electricity using fossil fuels burn the fossil fuel. And they will boil water, or they use some other mechanism to turn turbines, turn generators to make the electricity. And there's a fundamental limit of how much of the energy from combustion can you turn into the electricity. The fundamental limit is determined by thermodynamics. So if you put in 40 quads of primary energy, you get 15 quads of electricity, and you've lost 25. And that's lost. It goes into heat. Well, you can use the heat to send around into cities, and that's called cogeneration. But you can't get more electricity. 15 out of 40 is about what it is. So your power plant has a conversion efficiency of something like 33%. Now, renewables are actually, right now, not a large fraction of our primary energy. It's about 8% in 2010. In fact, this part of the renewables is hydroelectric power. Hydroelectric power has been around a long time, and the United States basically has maxed out on all of its hydroelectric resources. This is wood. I mean, wood has been a source of primary energy for centuries, and it's still, in fact, an important source. Here are biofuels, bioethanol, biodiesel. Here's wind, and here is solar photovoltaic. So wind and solar, which get so much of the interest in the press, and I'll have much more to say about them, they are tiny fractions of our primary energy, a few percent, in fact. Electricity is generated in the United States, as I said, mostly by coal, natural gas. There's nuclear. The United States generates about 20% of its electricity from nuclear power, roughly 104 nuclear power plants. And it's been about 104 for quite a while. There are two nuclear sites of construction right now, but unfortunately, due to cost, due to regulations, and in fact, due to economics, nuclear power is challenged in the United States, and for that matter, most of the rest of the world. I get this from Ameren, Illinois. You get the same thing in the mail. And this says, for the electricity that comes to your wall socket, what was this primary energy source? So here in our part of Illinois, Ameren, most of our energy comes from coal. There is some natural gas. There is some nuclear. And in fact, 7% of the primary energy that makes electricity that comes to your wall socket comes from wind. And that 7% actually is mandated by a state renewable portfolio standard. By 2025, it's supposed to be 25%. Okay, now I'm going to give you 3 points of reference that everybody talks about in the energy situation. Number 1, peak oil. What's peak oil? Well, it goes back to 1956. A petroleum engineer, King Hubbard, looks at the data of oil production from 1850, when oil production started, to present day, 1956. This is the production, billions of barrels per year of the world. This is production, billions of barrels in the United States. And Hubbard looks at that data, and he actually plots it in a different way. So this is what's called a log plot. And you see from roughly 1870 to around 1920, there's one slope. And then from 1920 to 1956, there's another slope. And Hubbard says to himself, this is going to turn over, and I predict that there will be a peak in the production of oil in the United States somewhere between 1965 and 1970. Now remember, this is the data he's looking at. Does it look like it's going to peak? And in fact, Hubbard's prediction was roundly criticized, ridiculed in fact. But these are data from our Energy Information Agency. There was a peak in 1973. And it is nothing more satisfying for a scientist or engineer to make a prediction and have it come true. Here's the next peak. And what's this peak about? Well, it's in fact the North Slope of Alaska, which Hubbard didn't know anything about yet. And now if we go forward to 2012, here's the hint of another peak. Let's see, that's the 1973 peak, that's the Alaska peak, and that's in fact another peak because, again, the United States is finding new ways to get oil out of the ground. In the petroleum business, the oil that you know that is there, that you can get out of the ground at a given cost, you call a reserve. But you also know that there's oil in the ground that you might be able to get out of the ground with new technology and perhaps a higher cost. And that's called a resource. And even around that, there's oil, or for that matter, coal or natural gas, that maybe there'll be a technology at a given cost that you can in fact exploit that resource. So more and more resources that become reserved, and the petroleum, the coal people, the natural gas people have been very, very good at developing new technologies. They have been very, very good at exploiting higher prices to get oil, gas, and coal out of the ground. Well, Hubbard said, you know, this is not going to last forever. Here's year 2000, and this blip here, that's going to be fossil fuel history for mankind. Now, I don't know exactly how wide this is going to be, but for sure, there will be an end to fossil fuels. Reference point 2, these are called stabilization pledges, a very clever idea that was put forward by 2 engineers at Princeton, Takala and Sokolow, and they want to help solve the energy challenge, reduce greenhouse gas emissions, and what do they say? Well, they say you've got fossil fuels going into power, transportation, and direct use, coal, oil, and natural gas. Right now, we're emitting 7 gigatons of carbon per year. Business as usual in 50 years would have that double. And that would be a disaster for the climate. Can we figure out a way to keep emissions flat in that 50 years? No. They're not even going to try to reduce emissions. They're going to try to keep emissions flat. And we'll see this in itself as a challenging problem. So BAU stands for business as usual. This is the prediction. Business as usual.
This is for the world?
This is the world, yes. So this is fossil fuel emissions from roughly 2000 to 2060. This is some model, not important. But this is the business as usual. And what they say is we're going to figure out a way that from 2005 to 2055, emissions stay flat. And using the principle of divide and conquer, they say this region here, so these are greenhouse gas emissions under the scenario of business as usual. We're going to figure out different ways, and they divided it up into 7. If you don't like 7, do 10 or 6. We're going to figure out ways, and the question is, how big is a wedge? Okay, so first of all, what is a wedge? This is emission rate. This is 50 years. This wedge is greenhouse gases that would be emitted under business as usual. What do you have to do for one wedge? So I copied down a few of their wedges. But first of all, is there a silver bullet? Well, as many people know from the Lone Ranger, there are no silver bullets in his ulcer. This is in fact a challenge, and here are some of the things that would have to be done for one wedge. But remember, we need 7 of them to keep greenhouse gas emissions constant. I won't go through all of them, let's just look at a few of them. Fuel efficiency. So if you had 2 billion cars, that goes from 30 mpg to 60 mpg. That's one wedge. If you had wind power from 1 million wind turbines, that's 50 times the wind turbines that are installed at the date that they did this, 2005. That's one wedge. If you replace 1,400 gigawatts of coal with natural gas, so that's 4 times the number of natural gas electricity plants, that's a wedge. If you could reduce the use of your electricity in the entire world by 25%, that's a wedge. If you could get ethanol from 2.5 million square kilometers, that's a wedge. That's 100 times the ethanol output of Brazil. If you could make 700 gigawatts of replace coal with nuclear, so that's roughly tripling the number of nuclear reactors in the world. That's a wedge. Looking at this list, we see this is truly a daunting task because we need 7 of these, and each of them itself is an enormous undertaking. So what Pakala and Sokolo have done is to show you how a seemingly impossible task is only very, very difficult. So what is the United States policy? Well, in 2009, before the Copenhagen meeting, it was reported that President Obama said that we will reduce our greenhouse gas emissions by the rate of 17% below 2005 levels by 2020, and 83% by 2050. So here's the United States. This is greenhouse gas emissions. This is right here in 2005, we're somewhere around 6 gigatons, and this now is actually carbon dioxide emissions. So the policy would be is that there's a 17% reduction in 15 years, and then you get really serious about the matter, and you produce a 83% drop by 2050. Now actually, the United States, I drew this little star here, the United States has had about 12% reduction in greenhouse gas emissions for 2 reasons. One, the economy has slowed, maybe not the reason we want. Secondly, a lot of coal plants have been shut down, and natural gas now is being used for electricity generation. So you can see there's been a considerable reduction of greenhouse gas emissions, but how you get to there is a major undertaking. In fact, this is an interesting plot. This says this bar is all of electricity generation. This bar is all of transportation. This bar here up there is residential and commercial heating. This, and this. This is 17% left over. So to get down to 83% reduction of greenhouse gas emission, you would have to zero out all of the emissions from electricity, all of the emissions from motor transport, and all of the emissions from residential and commercial heating. That's how big a task it is to get down to 80% reduction in greenhouse gas emissions. I'm going to go through this very quickly. In fact, let's just move forward. These are statements of our energy policy. I'll look at this one for a second. So a year ago, in the State of the Union address, what President Obama said was, happily, we have more and more oil production and natural gas, and now finally, in the last presidential State of the Union address, we must do more to combat climate change. I'm looking at the time. I don't want to keep you beyond. I'm going to just say that there has been an analysis of how much it would cost, and basically It's called a Stern Review. This is the most important sentence from the Stern Review that I can point to you. It says, what we do now can have only a limited effect on climate over the next 40 or 50 years. But what we do in the next 10 or 20 years can have a profound effect on the climate in the second half of the century. And that's the entire quandary we have as people, as nations, as individuals of this greenhouse gas emission energy climate problem. We would not see benefits for 50 years. And this is just not the kind of thing that we are accustomed to doing. Well, you know, there are people that say that the greenhouse gases aren't caused by humans. So what if it's a big hoax and we created a better world for nothing? Well, you have energy independence, you preserve rainforests, green jobs, livable cities, clean water. So maybe we should do it because we'd have a better world. Okay. Let me just say a word about the economics of electricity production. So there's a whole bunch of different ways you can make electricity, from coal, natural gas, and here's a whole bunch of ways from renewables, wind, biomass, and this graph here shows the cost. Levelized cost means you take into the cost of building it and the cost of running it. And the big difference between renewables and the fossil fuels is that renewables, the fuel is cheap, sometimes free, and for fossil fuels, the fuel isn't free. So this is the most economic natural gas-fired plant, and you can see that wind and hydro and biomass and geothermal have similar costs. If you take into account only the cost of making the plant itself, so-called capital cost. Watch that. Capital cost of all of these fossil fuel plants is much lower. And that's a serious problem because you've got to finance the construction, and if financing is tough, then you will go with what's cheaper. So the capital costs of all of these forms of renewable energies are now and have been still quite high. Ethanol, ethanol. Why do we talk about ethanol? Because in Illinois, it's ground zero for corn production. And there's lots of issues about ethanol. Is it positive energy production? Does it reduce greenhouse gas emissions? And actually, we are mandated to use ethanol in our gasoline. So this is called the Renewable Fuel Standard. In 2007, we have to ramp up so that in about 2012, 10% of our gasoline is ethanol. We consume 140 billion gallons of gasoline. We make about 14 billion gallons of ethanol. And in fact, farmers, producers have been successful in making ethanol. And this is supposed to ramp up. Now, the analysis of the energy balance for ethanol is done by a group at Argonne. And they start with the sun, they grow the corn, they produce the ethanol, and they put it in the refueling station. Or they start with the petroleum, they extract it, they put it in pipelines, they refine it, or they put it in the fueling station. And what do they find? So here it is. To produce 1 million BTU of gasoline, it takes energy about 0.2 million BTU. Put in 0.2, you get 1 million. To produce 1 million BTU of ethanol requires 0.8 million BTU. So there is a positive energy advantage to producing ethanol, but it's not, you'd like it to be much, much bigger. And it's not. Skip that. Here's a graphic. This represents 20 million barrels per day of US gasoline consumption. This represents what ethanol, in fact, does in gasoline consumption avoided. And you can see quantitatively, you know, all the 50% of our corn crop that goes into ethanol production is just not enough. Now there's hope to get ethanol out of grass. And in fact, this is a project at the University of Illinois for cellulosic ethanol. But so far, nobody knows how to turn grass into ethanol. Watching the time, I'm going to skip forward. Now let's talk about renewables. So why do we talk about solar and wind? And the answer is they are the most abundant of all renewable resources by far. So right now in the United States, total electrical consumption was about 700 gigawatts. Wind, 10,000 gigawatts available. Solar, 80,000 gigawatts available. So in principle, the energy is there. So here's the wind map. Most of the wind, in fact, is in the Great Plains, down into Texas. There's a surprising amount of wind in Springfield. This is offshore wind. Again, lots of resources for offshore wind. And this is electricity generation. This is the ramp of wind and solar. And in fact, if they kept up in this ramp in 2025, we'd get all of our electricity from wind and solar. But you know, we can't keep up that ramp. Now here's a sad fact about wind. So this is an interesting plot. It's the output of one wind turbine in North Dakota. And there's 8766 hours in a year. And you can see hour by hour, the wind power goes up and down and up and down. Now, suppose you took all the turbines around it. That's called a wind farm. And this is an interesting analysis. Each one of these dots represents a wind farm. And this is in the Midwest. This is in California. This is in the Northwest. This is in Texas. So this analysis takes every wind farm in the United States and asks how much power we can get from them. Well, I have to explain this graph for you. This is called the power duration curve. Now, what would you like of a power source? You would like 100% of the power to be available 100% of the time. And if you add up absolutely every one of these wind farms in the United States, what you find is only 13% of the wind is available for 90% of the time. And if you believe this, 6% of the wind capacity is available all the time. So you would have to have 16 times the number of wind turbines to have the complete capacity. The wind doesn't blow all the time, I'm afraid. So you got to store the energy somehow. And unfortunately, we don't have great energy storage yet. Here's one way to store energy. You take water from a low lake, you push it to a high lake, and you run a turbine. The closest one of these is actually in Missouri. There are some in California. Why can't we do this in central Illinois? We don't have any mountains. Another way to store energy is you can put gas into a cavern. Compressed gas is a way to store energy. And here's a project in Ohio that's been proposed. Or you can have batteries. Here's lithium-ion batteries, lead-acid batteries. So this is energy density. Way up there is gasoline. And this shows us that batteries are 100 times less energy carrying than gasoline. So right now, these are where our batteries happen to be. And for energy storage, we need something like factors of 10s or 20s. So I sometimes distinguish between technologies that need a breakthrough and technologies that need a miracle. And for sure, batteries need a breakthrough. Cellulosic ethanol needs a breakthrough. A few words about efficiency and conservation. So if you don't use the energy, then you don't have to produce it. And it's surprising to many people that individual and household energy consumption is 38% of our energy consumption. And that goes into transportation, mostly your private vehicle, It goes into all of your appliances. It goes into heating and cooling. So look at that number there, 43%. So if you wanted to reduce your energy consumption, the biggest thing you could do is to get a more efficient automobile. The next biggest thing you could do is to figure out cutting down on your heating and cooling. And in fact, there have been great successes in the efficiency of furnaces, air conditioners, and refrigerators. So over the last 3 decades, starting from some arbitrary point, your refrigerator now uses 25% less energy. So when you go to Sears or Best Buy or any of the stores, look for that Energy Star. That means that the appliance will use less energy and often considerably less energy. This is a real success story in engineering. Light bulbs. The incandescent light bulb is going out, and LEDs and compact fluorescents are going in. So here's a silly little calculation. Incandescent light, 100 watt equivalent, an LED only uses 13 watts. So suppose every household in the United States changed one 100 watt light bulb from an incandescent to an LED. And I did the calculation. We would reduce our energy consumption by 0.3%. Now, that sounds small, but remember, we've all only changed one light bulb. I think that's an enormous effect. So lighting, which is about 6% of your home energy consumption, there's great opportunities to reduce your consumption there. Insulation. You can insulate your attic, basement walls. And in fact, here's a little story. Plywood, brick, and straw. The insulation of straw, in fact, is just as good as the insulation of your fiberglass. And the pig that used the straw, in fact, made the most insulated home. Windows. Windows are a terrible challenge for energy efficiency. And why is that? Because you've got to let light in and out. Thermal radiation can transfer that. There might be leaks because the window has to open and close. There's convection and conduction. So windows are a terrible challenge for energy efficiency. There is a proposal for highly efficient energy efficient windows, but it has other problems. Transportation. So what about our cars? Our cars, this is miles per gallon. It's gone nowhere for roughly 3 decades. And you know a proposal from the federal government is to increase from roughly 25 to 50 mpg in the next few decades. And that would be an enormous change in our energy usage. So you could buy an electric car. And does that really save our country energy? Well, it depends. They claim you get 99 mpg from an electric car. And you can do the calculation. So this is the miles per gallon equivalent, fuel to the wheel. So your Nissan Leaf says it gets 100 miles to 34 kilowatt hours. I'll change that into miles per gallon. And then you've got to make the electricity. And remember I said the efficiency for making electricity was about 0.3? So if I put that 0.3, that 99 mpg goes down to 30 mpg. So we really haven't saved that much energy because of that conversion loss in the electricity. It's really not so much different than a conventional car. So, time's almost up. Again, there's lots that I couldn't put in. I didn't talk about fracking. I only mentioned nuclear power. If geothermal is your interest, that didn't get here either. I'm happy to answer questions after the talk, but let's come away with about 10 different thoughts. First of all, will we run out of oil, gas, and coal? And I think the answer is not for decades. The gift and curse of fossil fuels will be with us for decades. And this picture here is, in fact, the extraction of the oil sands in Alberta. Next, natural gas, in fact, is pushing out coal. It's making nuclear power plants uneconomic, and it's called a bridge fuel. So natural gas will replace coal in electricity, You could run cars off natural gas. It does continue the use of fossil fuels. And one problem with a bridge is that where does it go? Does it commit us to fossil fuels for decades and decades? Climate change is happening. More climate change will happen with business as usual. So this is a terrible plot that has what happens in agriculture, water, forestry, health. As the temperature gets higher and higher and higher, crop yields go down. Nothing good happens when the earth gets warmer and warmer. The United States actually is alone in its opinion about climate change, basically alone. Europe has climate change. The Chinese government now has seriously adopted renewable energy programs. Remember the wedge. Wedges are big deals, but it really, in fact, says that an impossible task is only very, very difficult. And we can't avoid this task. We have to take it on. Somebody has to figure out how to store energy, because wind farms, in fact, the power output wiggles up and down and up and down. This is the output from some solar array. And you'll notice that before sunrise and after sunset, you get no solar power. So without energy storage, serious amounts of energy storage, wind and solar cannot supply our total energy demand. There is, in fact, an opportunity to conserve and to be efficient. Roughly, it would save maybe 15% of our primary energy consumption if all Americans, in fact, insulated, bought their Energy Star, got efficient cars. It's both possible and desirable. All of that development of refrigerators, furnaces, air conditioners came because California and then later the federal government put forward a standard and a regulation, and standards and regulations often work. We've got to do something about all of the oil we use in our transportation. It is an outflow of roughly $600 billion a year from our country. I didn't talk about policy. There's two ways that you could go from fossil fuel generation to renewable generation using market principles. You could try to make renewables cheaper, and people do that. You could make fossil fuels more expensive, and they can be made more expensive by taxing. Once you put a tax on carbon, industry will be driven to try to develop cheaper methods to renewable energy. I didn't talk much about nuclear power. In fact, it has not, in fact, been the renaissance that some people have hoped for. Sadly, because nuclear power is the only large-scale, base-load generator of electricity that we know how to build now that has negligible greenhouse gas emissions. But do you want the wind farm, in Champaign County? Do you want the transmission line running south of Decatur? So, if not here, where's it going to go? We as a society have to confront the not in my backyard, and we have to realize that if you want to move from where we are, there will have to be accommodations. I think some new technologies will succeed. Biophysics, bioengineering, very clever people are working hard on trying to make biofuels. It is a real possibility for our liquid transportation fuel. This is a gorgeous focusing sunlight array, and in fact, focused sunlight does have inherent energy storage. This is one way, right with existing technology, that you could use solar power and store it for something like a dozen hours. So in sustainable energy, David Mackay says we have to stop saying no. No to nuclear power. No to the wind farms. No to the solar arrays. No to the transmission lines. We have to start saying yes to something. In fact, I say that we have to say yes to enough. And finally, which way do we go from here? It depends on which way we want to go. And we as a society, we as a world, we have to choose that direction, hopefully for the better of all of us. Thanks so much.